Okay, I guess in the interest of time, I know some people want to hit dinner or something later. I heard some comments here. I'm going to start the session, the second session on machine learning. I'm the session chair. I'm also the first speaker. So without further ado, this talk is about something that we like to call Jumpstart regularization. It's a slightly different way of training neural networks. And just to give you some context, because it's a very simple but very powerful idea, I'm going to tell a little bit about my journey from a discrete optimizer to a machine learner, because it feels that the CPAIOR is basically about that, given the two most common topics in the papers published here. So for a long time, my PhD, I completely ignored machine learning because I looked at backpropagation. That's not the kind of optimization I'm used to or that I'm comfortable with. But suddenly someone made me realize that if you look at a trained neural network, especially one with ReLUs, it's a mixed integer representable object. So you can do lots of things with that. You can do polyhedral theory. You can try to make it smaller. You can try to measure lots of different things. And suddenly I started having a lot of fun because I'm a very extreme discrete optimizer. I'm linear, deterministic, and discrete. But so I work on a few papers doing that. And 2 years ago at CPAIOR, I got this paper on lossless compression of neural networks, where the basic idea was to use integer programming to identify neurons that are always stable. They're always active or always inactive, because that gives opportunity for us to make the neural network smaller. But I was starting from the standpoint of, here's the neural network, it's trained, and then I do my thing. And that got the attention of this guy here, Carlos. He's at the University of Barcelona. He was looking at the same concepts, but he was trying to approach this problem in a very different way, which is, what if you try to adapt how you train the neural network so that we can actually prevent the issues of training networks that are very tiny? And that was a very interesting project. So I lost my fear of loss functions and training neural networks as we started working on that. So most of the sweat, tears, and interesting ideas that you're going to see about this paper are due to Carlos and Camilo. They're both PhD students at the University of Barcelona. I had the pleasure to work with them on this project. And also we have Eloi and Oriol, their advisors, who are also co-authors. So to give you the big picture here, what we're thinking about is, well, if you look at the way we train neural networks, we can train them in varying sizes and shapes, except if we want to make these neural networks too deep. And that's one reason why we have residual networks, because sometimes it's good to send like the signal to bypass the outputs of a layer, a few layers ahead. Otherwise, the gradient assign might be very loose, very weak. So if you go too deep, we might have issues. And also if you go too thin. And training thin networks is something I haven't seen a lot around. And our point here is that perhaps we would like to do both of these things, because because by doing that, we can create neural networks that are more expressive and also more parameter efficient. And in order to bring you to where the approach itself is very elegant because it's very simple, but to take you there to appreciate the ideas that they had, I'm going to go over a few other concepts to explain how a neural network, how we see these neural networks. So let's think about the simplest possible model of a neural network. Let's say we think about the rectified neural network, fully connected, where we have a mapping from an input space X to an output space Y. And every neuron has an activation function. So what happens in a neuron is that we're going to have this affine transformation of the inputs given by weights associated with every output coming from the previous layer, plus the scalar that is called the bias term. And the output of the neural network is going to be the maximum between this affine transformation and 0. So when the output is 0, we say that the neuron is inactive. And that mimics what you would see in biological neurons. So like sometimes they evaluate their inputs and they don't see anything useful that they would like to transmit forward. But sometimes they see something useful and they send something forward, which is the case when we have a positive output here. That's when we call the neural network, this particular neuron active. Now, what's very interesting about ReLUs is that this activation is the simplest activation that you can think in terms of, so let me rephrase that. In every neuron, we have to have some form of nonlinear function to make the neural network more expressive. And the ReLU is the simplest possible way you can imagine. It's basically a piecewise linear function for any pre-activation output that affine transformation I mentioned before, having a value smaller than or equal to 0, we basically output 0. For any positive pre-activation output, we have basically an identity function, and that's it. Now, what's very interesting is that if you pick a bunch of ReLUs and organize them in any way that you want, you're going to obtain a neural network that models a piecewise linear function, always. And so I think that's a very interesting way to look at rectifier networks, which is we're basically training, when we're training a rectifier network, we're basically performing, we're doing a sort of a piecewise linear regression. And each piece of this function is going to have a different pattern of active and inactive neurons. And if we have, the model is going to be a little more expressive if we have some variability in this pattern, if we're not seeing always the same neurons being active and the same neurons being inactive. For example, if all the neurons in your network were always active, that means we could collapse the entire neural network to a linear regression. So it's not as expressive. So I find it a little surprising and paradoxical that the fact that sometimes we censor the output of the neural network, instead of sending something negative forward, we send a 0. That actually is good because we are actually making the neural network more expressive. That is what allowing us to have different pieces in this piecewise linear function. Another thing that's important to mention here is that we can express more complex relationships if we have more depth. If you have a neural network with an input of size n, you need a depth of at least log n plus 1 to have every possible function being represented for that particular number of neurons. Now, just tapping back to John's talk earlier today, there's basically a combinatorial structure in the neural network here. There are some things that we learn about this combinatorial structure in terms of how many pieces this function can have. The number of these linear regions can grow exponentially. What we do know is that asymptotically, the wider you make the neural network, that's going to have asymptotically polynomial increase in the number of linear regions, in the number of pieces of this function. And the more depth you add to the neural network, that is going to produce an exponential increase in the number of these linear regions. By linear region here, what I refer here as a linear region is each one of these pieces of the function, of the piecewise linear function represented by the neural network. Now, what's also very interesting about these linear regions is the geometry that they define. So for every one of the neurons, we can define what we call an activation hyperplane. We basically pick that a fine transformation that happens inside the neuron before the activation. We equate that to 0. That's going to define for us a hyperplane. And one side of this hyperplane, we're going to have active points for which we're going to have a positive output coming out. And on the hyperplane and below it, we're going to have what we call the inactive points. The pre-activation output is going to be smaller than or equal to 0. So the output itself is going to be 0. And when we put together lots of different activation hyperplanes, we start to see how this piecewise linear function is going to define different, what parts of the input are going to define different pieces of this piecewise linear function. So here we have a very simple example from a paper we worked on 2018, where we have 2 inputs and then 3 hidden layers. Each of these hidden layers have 2 neurons. So that activation hyperplane that I mentioned before, in this very simple case where we have a 2-dimensional space, it's basically going to be defined by 2 lines. One of these lines is going to tell us that on one side, the neuron A is active. On the other side, the neuron A is inactive. Likewise, on one side, neuron B is active, and neuron B, on the other side, neuron B is inactive. And if we look at the output that is produced, when both neurons are active, this output is going to be 2-dimensional. And this is what we see in the white area on top here. When only one neuron is active, we're going to have like a 1-dimensional output. It's going to be a 0 and a positive number. And in this bottom triangle here, we're going to have both neurons inactive, which means for any input in that area, we're going to have a couple of zeros coming out of the first layer. And from that point on, we cannot really distinguish anything in this region. It's all going to be classified the same way by the neural network, no matter what we do. Unless you have some rectifier, you have some residual connections or other tricks. Now, what's also interesting is what happens when you look at these activation hyperplanes of the other layers in terms of the input of the neural network. Within each one of the linear regions that are defined by the first layer, we're going to see line segments here, which are basically the activation hyperplanes. But as we move around these different linear regions from the first layer, the segments are actually bending around, which is creating a structure that looks a lot like how when you transmit light across different media, as these things are moving around, And in terms of the output, we're going to see lots of areas getting darker, which means that the output is in a lower and lower dimensional space. And as we add more layers, we're going to see even more of that. And one thing that you're going to notice is that whenever some region becomes black, I can no longer partition it any further. Everything that falls there is classified the same way, has the same outputs. And also, like if you look at the gray areas, for example, I cannot partition them as much. Now, so this allows us to understand a little bit about each one of these parts of the inputs of the neural network. Another thing that's going to be very interesting for us here is to think about what happens when, instead of having the neurons having lots of different states, active here, inactive there, we actually have the neurons always having a particular state. For example, and this is from the CPAIOR 2020 paper. If we have an output, if we have a neuron that always has a 0 output, which means that this neuron is stably inactive, we can basically throw this neuron away because it's not doing anything for the model. And by doing that, we have basically the same model again. Now, another thing that could happen, especially in extreme cases with regularization, is that we could have a layer that is stably active. So all the neurons are always active. When that happens, the output of this of the neurons in this layer can be reframed as an affine transformation of the layer above this one, which basically means we can rewire the neural network and fold this layer. So we can get rid of an entire layer of the neural network, and the model is exactly the same. And then that brings us to the last case, which is a very extreme one, but it's a cautionary tale, and it's going to be relevant for what we're going to discuss here, which is we may have a neural network where an entire layer is stably inactive. If that happens, it means that the outputs of that layer are basically a vector of zeros. And being a vector of zeros, it means that the output of the network is constant, because everything that you try to put for the neural network maps to a single point in this layer and to a single output later on, which means you can just throw this neural network away. And what we're going to try to do here is not to throw the neural network away. So just for a quick recap, how does a neural network learn something, right? So we're given a training set. So there's going to be some inputs X mapped to outputs Y, and we want to mimic that with our model. We have some parameters theta that we want to adjust, and that are going to imply a prediction function, which is basically, okay, if you send some input for the neural network with this particular parameters theta, what is the prediction that we're getting? And we're going to have a loss function trying to measure the distance between the outputs that we expect and the predictions that the neural network currently produces. And basically, we have this optimization problem that we can solve by stochastic gradient descent, where we're minimizing this loss such that y hat here is the prediction for each one of the inputs that we have. Now, this constraint here is just syntax sugar. It's just because I find it easier to write this constraint than to write like one long line for an unconstrained optimization problem. Now, sometimes this doesn't work very well. Sometimes the machine doesn't really learn. There's some reasons for that. And what happens is that in the neural network either doesn't converge, which means we cannot find a local optimum for the training problem, or we find a local optimum, but when we look at the test data, it doesn't generalize very well. The accuracy is very low. There are many reasons why this could happen. Among them, it could be exploding and vanishing gradients those do not allow us to update the neural network properly during training. And we're going to be especially interested in the vanishing gradients. So one thing that happens is that when we have a ReLU, if the sample is not activated by the ReLU, that sample has no effect in the gradient update. And if you look at these regions that I mentioned here, that they're entirely black, there is no update coming from them. Any point that is using the train set and it's one of these black regions, it's not going to have any effect on the gradient updates when you do backpropagation. So, and that's an interesting thing here. When we think about the number of these linear regions that we can get, I'm very concerned about having zero-dimensional spaces close to the top of the neural network. When you think about gradient updates, if we have neurons that are never activated at the bottom, then we're not going to have any updates in the neural network at all. So, and this can be very bad depending on the choices of depth and width that you choose. So here I'm going to look at a particular example which is this Moon's data set. It's a binary classification problem. So I'm going to look at accuracy between 1 and 0.5, because when we get to 0.5, this is basically random guessing in a binary classification problem. So this is what happens with training. For different choices of width and depth, As you can see, if the neural network is very, very thin, we don't get very much from that. As we increase the width, we get better accuracy, and we get to a point where we can actually add more depth. But getting to more depth implies that we have sufficient width. And when we look at the validation or test, the accuracy is not going to be as good, but we can see a similar figure here. So then we wonder what could be wrong. Actually, Carlos had a very good idea of what could be wrong and a way to try to prevent that, which is we may have units that are dead. And when you talk about the dead unit, is like with respect to the training set. So that's a unit where for every input that we're using for the training, they're never making the neuron active. We can also have linear units. They're always activate, where for any sample they're active, which is not as bad, but it's not expressive enough. And then we have the nonlinear unit, which is the ideal one, where for some samples we're active, for some samples we're inactive. And that's not enough. They also had the idea of, okay, what if we classify the points of the sample? We could have some points that are dead. So no neuron in a particular layer is active for those particular points. We could have linear points. They're always active for the neurons in a given layer. And we can have nonlinear points. Sometimes they activate a neuron, sometimes they don't activate a neuron. And that's the ideal situation, because that's going to give us a very expressive function being modeled by the neural network. So, and to give you an illustration of like how these different states occur, we have here like we have like an analysis of what happens when you train a very extreme network on the Moon's data set, where we have 50 layers of 4 neurons each. So, and just because we had some issues with the figures, whenever you see a live, that means nonlinear. So at initialization, this is how it looks like. We get to a point here where it just happens that all the neurons are inactive for the samples that we have. And from that point on, we cannot recover and we cannot do backpropagation anymore. And after we try to train for a long period of time, like doesn't change much. So, and as you can see here, we're trying to classify between these 2 different half circles. And we basically guess that everything's the same. And if you think about it, what happens here when we have thinner and deeper networks is that we're going to be more likely to have a layer that's stably inactive. So if you think about it, for when we initialize the neural network, there is a certain probability that a particular neuron is not active with any of the inputs. As you put these neurons together, that reduces if you have a wider layer, that's going to reduce the probability that a particular layer is going to be entirely dead. But if you add more and more and more layers with the same width, this is basically a binomial probability distribution. Eventually, you're going to have a poor alignment of the weights, and we're going to have a dead layer, and then we're done. Which means that if we don't actively try to circumvent this, we can't train in any shape that we want. So, and the way that we're going to avoid this as discrete optimizers is with constraints, of course. So what we're going to do is for each neuron, we should be active for at least 1 sample. So we're going to pick the maximum pre-activation output for a particular neuron across all the samples. And we want this to be greater than equal to 1, which means we want to have a margin of at least 1 with the neuron being active. And for each neuron, we also want the neuron to be inactive for at least 1 sample. So we also want a margin of 1 on the other extreme with the minimization. And then in terms of the points, we do the same thing. Each sample should activate at least 1 neuron per layer. And each sample should make 1 neuron inactive per layer. This is going to cover all the grounds of these 4 different situations that we don't want to happen in terms of the samples and in terms of the neurons. And well, those inequalities I just mentioned, they're not syntax sugar anymore. So what we have to do is we have to dualize them, we have to put them in the objective function with penalties. And what you're seeing here is like the syntax sugar version where, okay, we associate a term with the violation or satisfaction of each one of these constraints. We put everything with an aggregation constraint as a second term of the objective function, along with the conventional loss function you would use. And then we're game. So we're back here with the baseline that I mentioned before, where we have what we can do in terms of training and validation for different choices of width and depth. And this is what happens when we use Jumpstart. We can suddenly train meaningful neural networks that are very thin, even like 1 neuron per layer, that have a reasonable accuracy. And as you see all over the place, like we're able to explore lots more shapes than we could explore before. And if we look back at that other figure about what are the states of the neurons now, what happens if we have just the unit constraints? That we're going to have some. We're going to have a little bit more of alive neurons here, and it's going to work almost well. So you can see that some parts we're classifying with a particular class, but I mean there are some parts where like the output is basically 0, so we're not really like, it's basically a coin toss between one side and the other. But the moment we add all the constraints, including the constraints on the samples, now we have, and we're talking here about a very extreme case because this is a neural network with 50 layers of 4 neurons each. You would never use it, it's an overkill. And you would wonder, this probably doesn't generalize well. It generalizes beautifully. So which is why I love these examples where you can visualize 2 dimensions. It's so we cannot see anything beyond 2 dimensions, right? So I have more computational results here. Here is like for CFAR10. We also tried some choices of depth and width. We tried more widths and fewer depths because it was a little more expensive in this case. And as you can see here, we do need a lot of width to get something closer to like 1 in accuracy for the training. And you see in validation also like we have similar figures. Now with Jumpstart, like for very thin neural networks, now we can have a decent amount of accuracy. In the case of CFAR10, having like a 0.4 accuracy here is not bad because CFAR10 has 10 classes with equal amount of samples. So random guessing would be actually 0.1. And here we have a few more results trying different configurations with different parameters for the aggregation function and for the penalties. And the one thing that we observe for CFAR10 is that if we group, if we look at these groups where we basically have about the same number of neurons. For example, here we have, for example, 20 neurons in 8 layers, or 20, or I forgot which one is depth and which one is width. Okay, no, this one is deeper. 20 layers with 8 neurons or 10 layers with 16 neurons have about the same number of neurons. If you have more depth with the same number of neurons, your number of parameters is smaller. And what we can see here is that in terms of accuracy results, we have about the same values. We see something similar between 20 times 32 and 10 times 64, and also like 20 times 96 and 10 times 192. So you can see that basically it's a little more parameter efficient. When we move on to CFAR 100, which we, because of time constraints, we were not able to do a lot of experiments. Okay, if you're trying a very narrow, very thin neural network, there was some difference here. But if you look at the case of like 20 times 32 and 10 times 64, the results are somewhat similar. And the one thing that you may notice here is that sometimes the accuracies are all the way down, which is the case of the baselines, where we don't have Jumpstart being applied at all, like which are the 2 last lines here of the legend. So as a conclusion here, what we did was we introduced a regularization for training neural networks, which successfully trains thinner and deeper neural networks. So we have more freedom to shape the neural network any way we want. And it generalizes well, even in very weird formats. Yields more parameter efficient neural networks for a given accuracy. And in a nutshell, what we're doing here is that we're preventing neurons from always being on and off or off. And we're preventing samples from making all neurons in each layer on or off. We're doing that by dualizing such constraints as penalties in the loss function. We're doing that because having a monotonous behavior in the neurons is going to limit what we can express with the neural networks, and therefore is going to limit our accuracy as well. And we do that when we want to train thinner and deeper neural networks, which I think it's a great direction if we want to think about like about models that fit well in embedded devices or in any device with limited resources. And so I would like to make a special thanks to National Science Foundation for funding the work I have been doing on that. And I have some references here that relate to the topics I mentioned before. These first 2 papers here about linear regions and like what you can different types of functions you can express with different architectures. And we have applied some solution counting here directly from SAT to MIP, which was very interesting for this audience, I guess. The next 2 papers about how can we make a neural network smaller once we have trained them. And shameless plug, we have this paper coming up at XML next month, where now that I'm not afraid of the loss function anymore, we look at the Taylor expansion of the loss function, and we try to use it to define a combinatorial problem for pruning multiple weights of a neural network. With that said, thank you very much for your time. Elias?
Yeah, thanks. I'll post that tweet. First. So if you change relu to leaky relu, or you add residual connections or something, then so let's say leaky relu. So you don't have the zero gradient situation. Does that, if you do 4 by 50 or just narrow but deep?
That's a very good point. I have no idea what would happen. What I can say that is that in terms of the expressiveness of the neural network, we're not going to have this loss of dimension so much. So we may have more pieces of in the piecewise linear function. So it's an argument for not doing things this way, for sure. Your question was the same? Okay. Yes.
So in the slide with the 4 results, the one with the constraint will solve with the optimal computation solver.
So, I mean, we talk about constraints, but we dualize everything. So it just becomes like an ordinary gradient descent application.
Oh, you gradient descent with the...
Yeah, I mean, we're just putting penalties in the loss function.
Oh.
The constraints are not there. It's just because I'm hardwired to think about discrete optimization problems with constraints. And with this audience, I think it's actually friendly to talk about constraints, even though at the end, we vanish with them in the loss function.
All of them are added.
And they're there.
Another question is, what does it imply to a network with increasing or decreasing widths? For example, an encoder or a decoder of a VA.
Ooh.
For example, if it's increasing width, then it's easier to be all inactive in earlier.
Oh, that's a very nice point. So the question, I just want to repeat that because so the main author is actually on Zoom. I think he might find this very interesting. So the question was about variational autoencoders, where you have like the narrowing of the width and then the width expanding again. And as you expand the width again, you're likely not to have like something very like you're not likely not to have a lot of linear regions defined in that part. So a very interesting question. I wonder this might give room to like a lot of discussion, especially like in the experiments, but I have no a priori guess of what this would imply. But that's a very good point. Yes.
You don't do any saddle point optimization, right? You just treat the Lagrange multipliers as fixed or something.
Yep. No, I actually don't know the answer for that. So Carlos, are you hearing us?
He's muted.
He's muted?
Yes, I apologize. Okay, can you hear me?
Yes.
Okay, what was the question? Sorry, because
there was a question if the weight of the penalties changes over time or if it's fixed.
It's fixed at this time. It's true that maybe since it's like a Jumpstart, it would be better like have a kind of warm up or something like that where you first feed the constraints and then you move to the cross entropy, whatever you're using as a main loss. But in this time, to keep everything simple, it's fixed.
Wonderful. Next question.
Does the sort of like optimal width to height change with the Jumpstart regularization?
You mean an optimal width and height?
So like assuming
of...
there's the same number of parameters, you can trade off width and height, right?
Mm-hmm.
And then without the Jumpstart regularization, I'm assuming you'll get some like width and height given some budget. And then with Jumpstart, you'll get a different one. And I was just wondering, does the Jumpstart sort of lean towards thinner and deeper, or?
That's the impression that I have from the results. That as we use Jumpstart, we tend to have a preference for thinner and deeper because it's going to give us similar results. We do want to do more extensive experiments in an extended version of this paper to understand what's the optimal point and like, to get more insights on like what are the constraints that make the most difference and how can we achieve the best parameter efficiency by playing out with lots of different things. It's kind of future work that we want to develop.
Is there any kind of overhead in training time?
Sorry?
Especially if you like apply this to much larger networks. Training time overhead.
If we can have overfitting for larger networks?
Training time.
Oh, in terms of like how much more, what's the overloading training time? If I'm not mistaken, the overloading memory and in runtime is about 50% because we're using the samples in a more expensive way. So yeah, there's a trade-off there. It gets more expensive to train these things. But then someone was telling me today, I think Paul was telling me that there is an understanding that actually like most of the time that the network is used is most of the cost of the network is actually on inference, not so much in training, which I found a bit surprising. But if that's true, it's not such a big deal that we're spending more on training here.